Let's explore Python generators, a powerful feature for creating iterators in a memory-efficient way. Generators use the yield keyword to produce values on demand, enabling lazy evaluation. Here is a simple generator example. We define a function called countup that takes a max argument. Inside the function, we initialize count to 0. We use a while loop to generate numbers from 0 up to max. The yield keyword returns the current value of count and pauses the function. Each time next is called on the generator, it resumes from where it left off. In the usage example, we create a generator counter by calling countup with a value of 5. Then we iterate through the generator using a for loop, printing each number. This demonstrates how generators can be used to generate a sequence of values one at a time, only when needed. So, what exactly are generators? Generators are special functions in Python that return an iterator. Instead of using the return keyword, they use yield. This allows them to generate values one at a time on demand. Importantly, generators maintain their state between calls, remembering the value of variables. The key benefits of generators include memory efficiency. Since they generate values one at a time, only one value needs to be in memory at any given moment. This approach enables lazy evaluation, where values are computed only as needed. This makes generators perfect for working with large datasets and simplifies the creation of data pipelines. Now let us see the syntax of generators using the yield keyword. Here's a code example. This defines a generator function called Fibonacci that takes a limit argument. Inside the function, we initialize the variables nb to 0 and 1 respectively, and count to 0. We use a while loop to generate Fibonacci numbers up to the specified limit. The yield keyword returns the current value of a, which is a Fibonacci number, and pauses the function. Each time next is called on the generator, it resumes from where it left off, calculates the next Fibonacci number, and yields it. In the usage example, we create a generator fib by calling Fibonacci with a limit of 8. Then we iterate through the generator using a for loop, printing each Fibonacci number. Key points to remember are: the yield keyword pauses the function's execution and sends a value back to the caller, but retains the state for resuming later. All variables and their values are preserved between yields, allowing the function to continue where it left off. Now let's understand the execution flow of a generator. First, you call the generator function, which returns a generator object. Next, you call the next method on the generator object. This causes the code inside the generator function to execute until it reaches the yield keyword. At the yield statement, the execution pauses, and the yielded value is returned. The next time next is called. The function resumes execution from right after the yield statement. This process continues until the generator is exhausted, at which point it raises a stop iteration exception. So the generator only runs when you call next, and it remembers its state between calls. Let us understand what is lazy evaluation. Lazy evaluation means that computation happens only when needed, not all at once. Values are generated on demand, rather than stored in memory. This is perfect for processing infinite sequences, large datasets, and streaming data. Here is an example: an infinite sequence generator is defined. Inside the function, we initialize number to 0. We use a while true loop to generate an infinite sequence of numbers. The yield keyword returns the current value of number and pauses the function. Each time next is called on the generator, it resumes from where it left off and increments number. This example shows how generators can be used to generate infinite sequences, computing values only when they are needed. The output of the code will be the numbers 0, 1, 2, 3, and 4. Let's explore some important generator methods. The first method is next. It executes the generator until the next yield statement and returns the yielded value. If the generator is exhausted, it raises a stop iteration exception. The second method is send. It resumes execution and sends a value back into the generator function. The value becomes the result of the current yield expression. Here's a code example. The echo_generator yields the string ready to echo. Then the value is yielded. The next line shows the generator is called and it prints ready to echo. The next print statement sends the word hello, and the generator prints you said, hello. The generator remembers the state. The next print statement sends the word Python, and the generator prints you said, Python. Let's explore generator expressions. Generator expressions provide a concise syntax to create generators, using a syntax similar to list comprehensions. However, instead of square brackets, they use parentheses. Generator expressions are a memory-efficient alternative to list comprehensions. This is especially useful for processing large datasets, chaining transformations, or when you only need to iterate once. A list comprehension is eager, storing all values, while a generator expression is lazy, generating values one at a time. Here is a code example. A list comprehension will store all the squares of numbers till 1 million. This would take more memory. But a generator expression will generate the squares only when asked for, making it memory efficient. Here is another example. This line filters and calculates the squares of even numbers from 0 to 9. This line sums all the numbers from 1 to 100 without storing all of them first. Let us explore an example where memory efficiency of generators is evident. In this example, we process a large range of numbers. The process with list function stores all the numbers in a list before summing them, whereas the process with generator function generates numbers on demand, one at a time. This approach dramatically reduces memory usage. You can see here the comparison between the memory usage of both methods. The list method takes about 80 megabytes, whereas the generator method takes negligibly small amount of memory. You can see the benefits here. You can process unlimited data streams. You can observe constant memory usage regardless of data size. There is faster startup time. Now let's explore how to chain generators to create data pipelines. This involves connecting multiple generators to perform a series of operations on a data stream. The operations include generating initial data, filtering the data to keep only what's needed, transforming each item, and then consuming the data on demand. Here's a code example. This defines a generator function numbers that generates numbers from 1 to infinity. The even filter generator will generate only even numbers. This creates a pipeline and displays the first 5 numbers in the pipeline. Here are some best practices and key takeaways. When working with large datasets, use generators to conserve memory. You can build processing pipelines by chaining multiple generators. When you need to iterate only once, prefer generator expressions over list comprehensions. It's important to remember that generators are single-use. Once exhausted, they cannot be reused. For complex generators, add proper documentation explaining the yielded values. The key takeaways from this are that generators enable lazy evaluation, computing values only when needed. The yield keyword pauses execution and returns a value. Generators are memory efficient for processing large data streams. You can use send to communicate with a running generator, and generator expressions provide concise syntax for creating simple generators. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.